In this video we're going to take a look at the Blacksmith challenge on HackTheBox. It's an easy Pwn challenge, and the description says, "You are the only one who is capable of saving this town and bringing peace upon this land. You found a blacksmith who can create the most powerful weapon in the world. You can find him under the label flag.txt." So let's begin by downloading the files. We'll get this working locally before we start an instance. And let's copy over the file to our local directory. And we'll start by doing some basic file checks. So as usual, we'll begin by checking the file type, and we'll see that it's a 64-bit LSB Pi executable. It's not stripped, so we'll be able to, it's not going to strip all the symbols and stuff, so we'll be able to statically analyze it a bit easier. We've got dynamically linked, so it's going to be using libc and things like that. And is there anything else we need to take note of there? I don't think so. So let's run strings -n10 Blacksmith, and if we go through here, as usual, we'll be able to see some functions, some of the imported libraries, and get an idea of what's going on with the functionality of the program. So we have some text here that it's going to print to us, and it looks like it's going to ask us some questions. We've got some options. Yes, everything is here. No, I didn't manage to bring them all. Let's not waste too much time trying to decipher what it's doing here, because it's going to be a lot easier to do that through decompiling it in Ghidra or by dynamically analyzing it in GDB. What we will do, however, is check the security protections on it. So we can do check sec file Blacksmith, and we'll see that we've got no NX disabled, so we are allowed to execute code. If we're able to inject code into the stack, we can execute it. We have Pi enabled, so we had Pi enabled, I believe, in the back computer challenge. If you haven't, if you're not watching these in order, I'd advise doing that. So let me actually just bring up a couple of links here. I'll bring one up on Pi. We also have canaries found. This is the first challenge that we've had canaries found, and we have full relrow as well. So I've described some of these protections in previous videos. Let me just open up a link to Ironstone's Gitbook here, where they describe Pi, and there's also good explanations here of stack canaries and how to bypass them. I'm not going to go through too much here because we don't actually need it for this challenge. The reason, I'll put these links in the description in case you want to check them out more, but actually we don't really need to worry about Pi or canaries for this. Because this is the first challenge that canaries have been enabled, I assumed that the goal was going to be to bypass this protection, but it's not relevant to what we need to do. So let's go ahead and just open this up in Ghidra and have a look at the code. We'll create a new project here, call it Blacksmith, and we can use a code browser here to open this up, and then we can import a file, import Blacksmith. Just let it do all its default analysis checks here. Yes, analyze, okay, it's all fine. And because this isn't stripped, we'll be able to see our functions in here. We can see a bow function, we can see the main function, which is where we're probably going to want to take a look at first. Again, we could have also gone in here and searched for strings and looked for any strings of interest and then tracked it from there. So there's a couple of different ways we can do it. Alright, so let's have a look at the code here, see what we've got. In our main method, we've got some variables that are declared at the beginning here. We have this local 10 variable, which is set up to equal the value here from the fs offset. So you can see that it loads. Let's go and we can see that it loads this into the RAX, and then it moves that value to the stack, and it XORs here. And then if we go to the bottom of the code here, essentially at the end it's going to load that value back from the stack into the RAX, and it's going to make sure that it's going to XOR, and it's going to make sure that these values still match. So that's the canary in place. If we were dealing with an actual buffer overflow here where we need to worry about this canary, we'd basically need to make sure that that value still equals the same value that it was assigned to once we get to the end of the function. So we need to find out what it actually equals, and we need to overwrite it with that same value in order to not trip off this stack protection. So with that out of the way, let's see what's actually happening in the main method. You can see here we have some text: "You're not worthy to carry this divine weapon and bring peace to our homeland. This is not a weapon, do not try to mock me." So these variables are just being set up so that they can be used, I guess, later. Where do we have that local 20? Alright, I don't see where it's being used here. Maybe it's being used inside of one of these functions. Oh, we have the local 18 that's being used here. You can see that it might write out local 18 saying this is not a weapon. But I can't see where the local 20 is. But let's not worry about it anyway. So it's printing out some information. It's going to take an input off us, and let's see here, local 28 is going to be an int, so we're going to give it an int, and that makes sense because here it's asking us, do you want to get supplier 1 or supplier 2? And then if we supply a 2, it's going to say farewell, come back when you have the materials. It's going to exit the program. So we need to supply a 1 and say we have all the materials. And if we supply a 1, it's then going to ask us, it's going to print this out. Let's have a look at the, let's have a look. It's going to print this out saying, what do you want me to craft? 1, 2, 3. And the 2 equals a shield, the 3 equals a bow, or a 1 will equal the sword. Anything else will cause this to exit. So let's have a look through these one by one and see which ones are going to be of use to us. We'll start then with this shield function. Let's go in here, and we have the shield function. Again, we have the stack protections set up, which is going to set this up at the beginning. It's going to check it at the end. We have this is getting the string length here, so it's making sure that whatever's written here is going to equal the length of this data. And what does the data say? It says, excellent choice, this luminous shield empowered with the sun's light. It will protect you from any attack. And then it asks us, do you like your new weapon? And it reads an input from us. The input it reads is into this local 58 variable, which is 72 bytes, and it's reading in 3f bytes. So it's reading in 63 and into a 72 byte buffer. So there is no buffer overflow here, but what we will notice is that the value that it reads in is going to execute as code. So although there's no buffer overflow there, we're essentially given direct code execution. So that's very interesting, but let's go back and check out the other methods and see what's going on there as well. We go and have a look at the bow. The bow will, so the bow takes no input. All it's going to do is write this out. So that doesn't appear to be of interest. It might just be here to kind of obfuscate the actual area that we need to focus on. Let's have a look at the sword as well. And the sword is the same. So the sword just prints out these values. It doesn't take anything from us. There's no buffer overflow issues here. So let's just verify this by going back to our function which does have the read call in it, which is the shield function. If we go to the read call, go to the read call here, and we can look for references. We'll show references to read, and we'll find there's an unconditional call right here, but that's the only call within the program to read. So we know that's the only place that we're going to be able to, in this case, not overflow the buffer, because we know that the buffer is big enough for our input, but in this case it doesn't matter because it's going to be executed directly as code. So let's go and run the program, have a play around with it in GDB, and then we can start putting together an exploit in PwnTools. So let's run the program here. Let's do chmod +x Blacksmith, and we'll run that. And we know from our Ghidra analysis now that if we hit 2, it's going to exit the program. It's going to say come back when you have all the materials. So we need to hit 1. I'm going to say yes, everything is here, and then we have our option for our shield. We have our option for our sword, I believe, or no, our bow, and then our sword, I think. So we can do, let's do them in. We know that 1 is the one that's going to ask us for an input, so let's start by doing 3. We'll see, yeah, okay, bad system call. That was for the bow. Let's do that again for number 2. And, oh, okay, this is the shield. Do you like your new weapon? And this is where we might say, this is where whatever we enter is going to be executed as code. So you can see here it's seg faulted, not because we overflowed the buffer, but because we inserted some code which isn't valid. And similarly then, if we would have selected 1, it'll just come back bad system call, this sword, etc. So 2 is the one that we need to focus on. Let's open this up in GDB. So GDB, PwnDbg, or Jeff, or whatever you're using, Blacksmith, and we can have a look in here at the same sort of stuff that we saw in Ghidra. We can see our functions, we can disassemble the shield, oops, not in capital letters, and have a look at the code here. We can go and set breakpoints up and stuff. Notice that the addresses aren't populated because it's using Pi. They're not going to be populated until the program actually runs, in which case we'll use things like Pi base to identify what the base is. And I think back computer again, if you go back, we did some stuff with Pi base in there and calculating offsets based on that. But we don't need to worry about that in this case. So let's just look what else we could do in here. We could try and get our ROP gadgets if we needed some. We could type PwnDbg to get a list of different functions that we might want to call. For example, radar. And then we could analyze the functions. We can do AFL to list them. We can select one, smain, and PDF to disassemble it. We can have a look at the sections, I capital S, have a look at the sections. There might be some sections here that we want to write some data to. So we might need to see how much room there is and whether it's writable, whether it's executable, and things like that. Alright, so there's my usual rants out of the way. Let's try and let's just see what happens with the cyclic pattern, because there is no buffer overflow here. So let's just try and approach this as if it were, and as if we were trying to find a buffer overflow. We'll run it. We'll select. Actually, let me just hit Control and C to cancel that. And now let's have a look at our Pi base. You can see there it's identified the base. If we wanted to find some functions, we could say print system. You can see here our libc system address. Again, if you want to print read, you can see our read address and things like that. Okay, let's continue the execution. And it asked us, we need to enter a 1, we need to enter a 2, and now it's asking us, do you like your new weapon? So we're going to paste in the cyclic pattern. And you can see here we got undefined command, could not read memory address, but it doesn't have. See here we have could not find elf base. We don't have a cyclic pattern here that we can search for because we didn't overflow these registers with our values, essentially. So that's that out of the way. We know that we can't do our usual cyclic pattern find in there. We'll also have a look at doing that in PwnTools and just see the difference there as well. But let's move on to doing this in PwnTools. So I'm going to copy the PwnTools template. I'm going to call it exploit.py for now. And let's open this up in Codium. Right, so let's do our usual checks in here. We need to do our usual stuff, so we'll set this to the correct binary. We'll put in Blacksmith. This is going to grab the context for us, so it'll know what architecture, what bits, what operating system, and it'll take care of all that for us throughout the rest of the program. Let's take out this write payload, because we're not going to need that for this example. And okay, so presumably if it's executing some code, we might be able to execute a shell. We might be able to use shellcraft, which we used in, I can't remember which challenge, but a couple of challenges ago we also used that. Before we do that, let's see what happens if we comment all this out, do our cyclic pattern. We know that whenever we run, it's going to ask us, we need to press 1 and then 2, so let's do that. We'll press 1, then we'll press 2, then we'll send the payload. Let's set this to debug so we can see what's going on. And if we try to run that now, Python exploit. Okay, that's a different error. That's because we haven't set this for 64 bits, so it's currently trying to read the offset from the program counter, the instruction pointer, rather than from the stack, which we need to do for 64-bit. Let's go back, do that again. And now we get a different error. So we have non-type object has no attribute read, and there's the issue. It couldn't find a core file because the program didn't crash. We didn't overflow the buffer. So there's no offset for us to find. There's no pattern. We don't need to worry about that at all. Let's go and comment this out altogether. and let's start working on our payload. I'm gonna okay, yep, alright, we'll just uncomment this stuff. And let's put in our correct options first. We need to press 1, we need to press 2 before we send this payload off. So just paste that in there. We'll change these to IO. Alright, now we just need to get this payload built up. And depending on whether we're getting a shell, or let's do IO interactive first of all. So if we want a shell, we'll use IO interactive. If we want to grab the flag, we'll use this instead. And to create the payload then, because it's just executing code, we're going to use shellcraft. If I type shellcraft here, I don't actually get any autocomplete, which is really annoying. I'd love to find a way to do that in Codium. But what we can do is we can do shellcraft here in the command line. See here it comes up with, we can do -h and then pass in, I guess, one of these things to find out more about it. So we can do, let's try -h cyclic. Okay, -h just gives you a generic help menu by the looks of it. Let's list. We want to list the available shellcodes. So we'll do shellcraft-L, and we get a list of all these functions. So these are functions that we can basically, in here we can say shellcraft.linux. Whatever we need to from here. In fact, we don't even need to worry about saying the .linux, because we've defined our context here, and they know we're using Linux, they know it's 64-bit, they know it's little endian. We don't need to worry about all of that. So let's see if we can list these and grep out. We'll grep out Linux because we want Linux anyway. We want to make sure it's available in Linux. And if we find something here, let's say the sh, although it's for thumb, AMD64 sh, this would be a shell. So can we do, let me see, if we pass that there, so that prints that out in hex, I guess. I'm not too sure exactly what the syntax is in here, but if we wanted to encode it, where's our output? Okay, we can output in whatever format we want here. So let's do, we could do -f A to get assembly code, and we'll get the actual assembly instructions here. We could put it in different formats, and we could go and basically paste it into our exploit.py. If some of the functions take parameters, it'll also let us know here, and we can pass in the parameters along with it. But for now, we don't even need to take this. I'm just giving that for a demonstration, just to show how to find what you're looking for there. Now we can just say, well, we know that this sh function exists. We know it doesn't take any parameters, so let's just say our shellcode is equal to this. But we also need to put it into ASM. Let's do ASM here. This is going to run this function cpp over given shellcode and assembles it into bytes. Cool, as our shellcraft then. Another thing we could do, let's go to, there's plenty of documentation on PwnTools and shellcraft and things like that, so you can go and have a look at the docs and go and have a look at the different functions and how to use some of them. On here there's plenty of documentation. So we have no offset here to worry about. You see we had the offset here last time. So what we could actually do here, rather than even building the payload, why don't we just send the payload here and say the payload is equal to flat shellcode. Because that's all we're doing here, and it's not like we're going to need a pile of parameters here. We don't have any offset, so that should be fine. And then IO interactive to get our shell back. So let's try and run this and see what happens. Close this. Yeah, we'll close that down for now. Run Python exploit.py. We get this interactive here, but we do see that it stopped with the exit code -31 sigsys. Okay. So if we go back to our challenge description, it did say here you can find him under flag.txt, indicating that maybe we don't need to get a shell in this case, that we're actually trying to just print out the flag. So we could go back here and say, let's say shellcraft io.cat, shellcraft.cat, and then pass in flag.txt, and then instead of doing the IO interactive, we could try and retrieve the flag this way. Let's try and run that. Okay, don't seem to receive anything back. We could double check and just add another print io.receive. No, okay, end of file. So we didn't get anything back there. So what we want to do is have a look and see if there are any seccomp protections that are preventing us from doing this. To do this, I'm going to use seccomp-tools. Let me open up the GitHub here. You can install this using gem install, but if you go and have a look at the GitHub, it'll say that the project is targeted to but not limited to Analyse seccomp, sandbox, and CTF Pwn challenges. Some features might be CTF specific, but still useful for analysing seccomp in real cases. And the features we have here, we can automatically dump seccomp BPF from execution files. We can convert it into human readable format. We can write seccomp rules, etc. If you have a look here, yeah, we can do gem install. If you have any problems, do this sudo apt-get, and then here's the instructions on how to use it. So what we're going to want to do is try and do the dump and have a look at this. Let's go back, and actually if you also have a look LDD, Blacksmith, we'll see here compared to the last ones which had libc and stuff linked, we also have this libseccomp linked here, and we can also see this within Ghidra as well. If we go and have a look through, you can see we have our seccomp section with, you can see there the load, rules, add, so rules are being added here. But let's go and try and dump the rules from here. So we can do sudo seccomp-tools, and then we want to dump, and then we'll pass in Blacksmith. We could go through the different options here. Let's do no, I did not manage to bring them all. That's okay, it just exits. What we want to do is have a look. Do 1, we'll hit 2 for the option where we're able to put in the input, and here you can see it dumps out the seccomp rules. And what's it saying here? It's saying if the architecture doesn't match, go straight down to 010, which is going to return kill. It's going to kill the program. And then it's going to go through these step by step. So it's going to check the sys number. Here it's going to make sure that it's within this range, and if it's not, it's going to kill the program. And then it's going to check to see what functions are being called. If the function being called is either read, write, open, or exit, then that's fine. It's going to go to allow. But if it's anything else, it's going to return kill. So if we try and put in cat, like we just did, or if we try and put in a shell, like we did before that, they're not valid, they're not allowed. So we need to focus on using these function calls, which makes sense because of our challenge description. I'll put this link in the description, by the way, to the seccomp-tools. But our challenge description says that we can find under the label flag.txt. So these functions have been allowed, so what we're going to want to do is try and open up flag.txt, read some bytes from it, and then write those bytes to the standard outputs. So open the flag.txt, read the flag, and then write the flag out to our output. And all those functions are allowed, so we should be able to do that. We can go back to our shellcraft and do shellcraft-l, and then we could grep Linux. Let's grep Linux again, just see what we've got here. So we have our, let's grep open. So we have for some different architectures here, and we could get an idea as well if we, let's say this open file option, if we do shellcraft and then just pass that in, it's going to come back with an error. And okay, let's try and do the open. I just want to get an idea of it showing. Showing that we can, that it'll tell us what parameters we need to provide. So you can see there, whenever I try to run that, it'll say nope, this takes at least one argument, so we need to obviously provide it the flag.txt. Oh, we mean, okay, yeah. So this isn't a valid architecture. So the way I went about this was, rather than, we can identify that these exist in shellcraft here, but we can just call shellcraft and let PwnTools worry about getting the architecture and stuff like that. We can call that from here just by doing this shellcraft. So if we were to say shellcraft open flag.txt, that's fine. And if we need to add some more to this, so let's go and have a look at some documentation. We can go and have a look here at the read documentation and see that read takes in the int file descriptor, takes in the buffer that you want to read, and then the amount of that you want to read. So if we go back here and say shellcode plus equals, let's append this, we need to compile it as well into the bytes, and ASM, and we'll say shellcraft dot read, and then so let's go and have a look at the Linux man pages here. If we search read, and we'll see that we can use read2 to read from a file descriptor, or read3 to read from a file, which sounds good. So we can go and have a look at the documentation. We'll see that it takes in the file descriptor here. 3 is going to be to read from a file, and then it takes in the buffer that you want to read, and then the pointer to the buffer, and then the amount of it that you want to read. So if we go back here and say we want to read 3 because we're reading from a file, we're going to read it to the RSP, to the stack, and then how much do we want to read. So this doesn't really matter, the flag's not going to be too long, but we can put in whatever value there. And let's do shellcode plus equals ASM. Finally, what we want to do is write this to the output. So if we go and have a look at our documentation again, search for write, we can see that if we want to send a message to another user, for us it's going to be write1, because we want to write it to the standard output. So let's go back to our code. Let's do shellcraft.write, and then we can put in our file descriptor 1, and then we're going to say RSP, and then here we'll have RAX. So we're going to open the flag file, we're going to read the flag out of it, and then we're going to write that to the screen. And hopefully, if we go back and try to run this, we'll get an error. Did we create a flag? Let's create a flag, subl flag.txt, and we'll put in here flag, fake flag, save that, it's flag.txt. Pretty sure I told them the file name right here, but okay. And let's try and run it again. Oh, not run that again. Let's run the exploit again, and you see that we've retrieved our fake flag, which is awesome. Let's go and we don't need to print this then. Let's go and just set that to IO receive, and let's try that again. And there's our flag, looking good. So now we need to test this out against the remote server. So let's go and spawn a instance. Might take a little while to get going. We can take a copy of this, and because of the template we're using, we can quite easily just run the exact same thing again, but we'll add remote in capital letters, and then we'll paste in the address followed by the port. We run that, and we get back our flag. So that's been the Blacksmith challenge. Hope you've enjoyed this video. If you have any questions or comments, if you've got any tips on how to do these Pwn challenges better, or how to use PwnTools better, I'm always looking for any cool tricks or shortcuts here, or just other ways of doing things. And as usual, I'll put this script on GitHub. And yeah, thanks for watching the video.